Right, let's talk about some reactions of alpha-beta unsaturated carbonyl compounds. When I talk about alpha-beta unsaturated carbonyl, what I'm saying is this is the carbonyl group, and this is defined as being the alpha group and the beta group. We talked about this back in test 2 when we were discussing the positions of carbons in relation to carbonyl groups. And the carbon next to the carbonyl group is typically called alpha, and the next one is called beta. So this would be an alpha-beta unsaturated because of a double bond, and the carbonyl group. You'll notice this is a conjugated set of double bonds, which means it has a specific set of reactivities that goes along with that. When we're discussing the reactivity of this system, it's typical to number the system. We number the system from 1 here on the oxygen to 2 to 3 to 4. This has nothing to do with the numbering system we use for naming. This is strictly numbering the alpha-beta unsaturated carbonyl system. So we have two kinds of addition that can occur to this alpha-beta unsaturated carbonyl system. The first one is called 1,2 addition, which is attack of a nucleophile on the C double bond O. And we just get attack on the C double bond O. That's 1,2 addition. We can also possibly have addition, though, on the 4 position of the carbonyl system, of the alpha-beta unsaturated carbonyl system, and that would lead to what we call 1,4 addition. Now this will occur depending upon the reagent that we use. If we take a look at the different kinds of reagents, we've got two possibilities here. We've got the lithium reagent. Since lithium is a very small positive ion, you look where it is on the periodic chart, it's about 3, so you'll see that that's going to be a very small cation. That means that the anion that corresponds to it will also be small as well. And since this anion is small, we're going to call it a hard charge because the negative charge is very concentrated around the nucleophilic center. When we take a look at the alpha-beta unsaturated carbonyl system, we also notice that we're going to have a higher positive charge next to the oxygen and a weaker positive charge down here on the 4 position of the system. And this is going to lead to a more diluted type charge down here and a more concentrated charge up here. So down here we can talk about the copper lithium nucleophile, and the copper lithium is a very large cation. We know that where copper is on the periodic chart, it's about 29, so we know that that's going to be a very large cation, which means that the anion next to it will be correspondingly large, and the negative charge will be fairly well spread out or diluted. And what we notice is that hard charges tend to react with hard charges and soft charges tend to react with soft charges. Concentrated charges like to react with concentrated charges, and diluted charges like to react with diluted charges. This is a very simple way to explain a very much more complicated set of circumstances. But the reason I'm telling you this is so that you can get some appreciation for why the alkyl lithiums will attack at this carbon while the copper lithiums will attack at this carbon. Right, let's take a look at two examples. Here is an alkyl lithium, and the alkyl lithium will attack at this center here, and I'll show you the mechanism for that. The CC double bond will remain unaffected by this, and we're going to treat the alkyl lithium just as we would a Grignard reagent. We'll take the metal off and we'll put the negative charge on the C to which the lithium was attached, and we'll have that come in and attack the C from the C double bond O. Electrons jump up on the oxygen, and that will give us that. The double bond is still here, and then we can add H plus in the second step, and we will end up with this compound. Now, we were introduced to copper lithium reagents back in test 3, and we were looking at the reactions of these with acid chlorides, and we were able to make ketones with these. And the reason we were able to do that is because this was a much milder reactant than, say, an alkyl lithium or an alkyl magnesium bromide, like a Grignard reagent. And VAD is also playing into this as well. But one thing we had noticed was that when we used this reagent, only one of these alkyl groups actually gets used. So I can draw this, and I'll draw the alkyl group very much in the same way as I did previously. And again, we're just looking at the alkyl group with the and the copper is connected to this carbon, so that's where the negative charge will appear. Alright, so this comes in, it attacks at this carbon, and then the double bond moves up to this position and pushes these electrons onto the oxygen. And that's how we get attack at the 4 position. Alright, just going back briefly to the PowerPoint, you'll notice that the alpha-beta unsaturated carbonyl system we've been discussing is capable of resonance, and that resonance leaves a partial positive charge on this carbon at the end of the system at position 4. So that's how I'm justifying the attack of this negatively charged species on that carbon right there. Right, then we can have the H plus come in, and we get what's called an enol. And what we know about enols is that they are in equilibrium with their ketone counterparts. And this is how you can get a ketone out of an enol. And this explains why we end up with the product that we do. Alright, so as you can see, what's happened is that we have had attack on this C, which means we lose this double bond. Now in the process, we get this enol, which then converts into the ketone. Now this is actually in equilibrium, but there's probably just a very tiny arrow going back to the enol here. Anytime you've got a ketone, you've always got a little enol in there as well. Alright, so that explains why we're doing this. The other thing I just want to point out again is that when we've got the copper lithium, even though there's 2 alkyl groups attached, only one is active, just as it was when we were reacting it with the acid chlorides to form the ketones back in test 3.